So we want to write the equations for slope and displacement. We know they're related. But the first thing to do would be to write an equation for moment. As we just discussed, you can write a continuous equation for moment. You might also recognize that we had to write moment equations, shear force and bending moment equations for the first part of the course. Now that's kind of the first step in some of these problems. So we'll get started. So I like to kind of imagine the beam cut somewhere, like maybe here, and then ask yourself, do you want to work the left side free body or the right side? I think in this case it's a little slight advantage to work the left side. So this would be at some distance x. Of course, I draw my free body diagram here in a second. Look at the internal bending moment as a function of x. So if I do that, I need to find the reactions at A. So I'll quickly come over here and draw a little free body diagram of the structure. Assume a reaction at A acting up and one at B also acting up. Instead of dealing with the distributed load in that form, we'll deal with the concentrated equivalent. So it's a rectangle. We know there's a rectangle, base times height. So this particular force will be WL. And it happens through the centroid. The centroid's right in the middle, and that'll be L over 2. So you're probably already guessing what the reactions are going to be. But I'll go ahead and do a quick calculation just to verify. So we will sum moments about B, make sure it's equilibrium. And when we do that, the only unknown we'll have will be AY, which we've already talked about that. So about B, our concentrated equivalent force creates what kind of moment? Positive or negative?
Positive.
Positive. So the force is WL, and the moment arm is L over 2. And then the reaction, AY, what kind of moment does it create? Negative. So that's AY is the force, and the distance is L. So I think you can see that the force is just going to be WL over 2. Kind of what we thought. Basically, half the force went to one side, half will go to the other. Now with that done, I'll come down here and look at a free body diagram of my left side that we talked about. I'll go ahead and apply the force we found, which was WL over 2. And at this distance x, what do we have? We've got the internal shear force. That's a positive shear force. And there's my positive bending moment. Now, we don't really care about shear force. We're only really concerned about bending moment right now. And then this this distributed force becomes what? Well, the area of that curve would be base times height. Base is x, height is w. So the force is going to be wx. And what's the distance from the cut to the centroid? Yeah, half the distance, or x over 2. So I'll now sum moments at the cut, make sure I'm in equilibrium. And when I do that about the cut, I have the actual moment, which with my sign convention will be positive. This concentrated equivalent force about the cut, is that positive or negative moment? Positive. So the force is Wx, the moment arm is x over 2. And then I have the reaction, which creates negative moment. The force is WL over 2, and the distance is x. So just solve for the moment. So my moment as a function of x will be equal to what? It looks like this first term is wx squared over 2, so that'd be minus wx squared over 2. And the last term will be WLX over 2. We can tidy things up a little bit. Each of them have a common W over 2. I can pull that out. And then I'm left with LX minus X squared. That's my equation for moment. Can I check that? Do I know some couple places where the moment's 0?
Yeah,
A and B. So what's the value of X at A? That's 0. So at X equals 0, the moment should be 0, and is it? Yeah, you put 0 in here, you put 0 in here, it goes to 0. Also at X equal L, the moment should be 0. And if you put in L here, you get L squared minus L squared, 0. So it seems to work. So we have a good moment equation. So in part 1, exam 1, you're done. Of course, I'd never given you this easy a problem for exam 1, but you would be done. So now what do? Integrate that thing. So the first integration will yield the slope. And remember, it's the moment divided by EI. And EI will assume is constant. I've also got this W over 2, so I'm going to factor that out. So I'm going to have W over 2EI. And then the integral of my moment, which will be LX minus X squared dx. That's pretty cool. So I think you guys can do that. So it looks like W over 2EI, that stays there. And then I'll have this integral, that'll be LX squared over 2 minus X cubed over 3. And this is not this is an indefinite integral, so I pick up an integration constant. I'll call it C1. So there's my expression for slope anywhere in the structure as a function of x. Do I know anything about slope just looking at this problem? Yeah.
You always divide by EI?
Yep.
On the slope equation?
It's m over EI, right? The integration is m over EI.
Okay.
Remember those? That was the fundamental, what we call it, simple beam theory.
Okay.
Actually, the second derivative of displacement is equal to m over EI. But if you integrate it once, you get slope. You integrate it twice, you get displacement. So if you look at these boundary conditions right now, or these supports, we know at A, what do we know about what's happening at A in terms of the slope and displacement?
Nothing.
Well, something. We know displacement is, well, nothing in that there's no displacement.
Right.
There's something happening there. Displacement is 0. What's the slope? I don't know. Something. Not non-zero. And you go over here at B, you have the same thing. So those are going to be my two conditions. So really right now, I can't really do much with my slope equation. I'll just leave it alone. So I integrate it again. I know that y is going to be the integral of the slope. And there's my y expression, so I'm going to integrate that. So I'm going to get W over 2EI. That hasn't changed. And integrate this. So I get WL cubed over 6 minus x to the 4th over 12. I'll integrate C1. That'll be C1x. And then I'll get a second integration constant, C2. So now I have one expression for my displacement in terms of two constants, but I have what? I have two boundary conditions. So let's apply those. It's probably a pretty good idea to always apply the one that occurs at x equals 0 if you have that opportunity. Because when you put in x equals 0, a lot of terms in your equation are going to drop out. So I'll do that one first. I know that y at x equals 0 is equal to 0. So are my conditions. So you put in x equals 0 here, 0, 0, 0. What are you left with? C2. So to make it fit, then C2 has to be 0. Is C2 always 0? No.
Just that when X.
On this particular problem, it is. So now what do? I got one more place too. This is when X is equal to L. So let me give myself a little more space here because I'm going to get all kind of jammed up here if I'm not careful. Let me do it over here. So at y equal L, I know it's also 0, but what do I get? Well, I got to plug in L in here everywhere. So I've got my constant sitting out front, W over 2EI. And let's see what we get. So I put an L here, I get L to the 4th over 6 minus L to the 4th over 12. What's that? That's L to the 4th over 12. And then I get plus C1L. And all of that has to be 0, so that means you have to solve for C1. So what is C1 going to be? Looks like it's going to be negative WL cubed over 2EI. You see that? Oh, yep, you're right. How do I get a 4 in there? I can't. Oh, that's too bad. I'll scratch this 2 out, and I'll write 24 at the end. It's ugly, but it's effective. A lot like the way you guys work tests. No, you did great. So what would be the final solution to the problem? The problem would be my equation will be this. So I know C2 is 0. I know what C1 is now. I can plug all that in. You can probably make it look a little prettier, but I won't. I'll just do it like this temporarily. So I've got this value times this, which is L cubed over 6 minus L to the 4th over 12 plus C1x. C1 is this value, which is minus WL cubed, see if I can get it right this time, over 24EI x. Now you can start manipulating this a little bit if you wanted to. You'll notice that everybody's got a W. Also, this 2 times 6 is 12. This 2 times 12 is 24. There's a 24. You can probably work on this and get like a WL over 24EI factored out if you wanted to, but you don't have to. But it's very common to do that. In fact, if we looked in our book for the solution to this problem, which I'll just kind of slide it over here for a second. It's this problem right here. And if you look all the way down there on the end, you'll see, again, D, kind of an odd term. But you'll see there's a WX over 24EI, and it's been manipulated. But we have pretty much those same terms. So it's very common to try to find this common factor and pull it out. But it's not required. We also have an equation for the slope, right? There was our slope equation, and we know what C1 is. It's the same value. I could plug that back in there, and I have an equation for slope. So where does the maximum displacement occur? Right? So if you know where the slope is equal to 0, that's going to probably tell you what? Where the displacement is max. Or it could be a min. But in this particular problem, I think from our previous work, you're probably going to realize that our displacement is going to look something like this. And it'll probably occur somewhere in the middle. In fact, I wouldn't be surprised if it occurs right in the middle. And if you were to go up here and put in L over 2 here, I imagine this would go to 0. And you find that, in fact, it is true. But you could always do that. You could always compute where the slope was 0, use that value of x in your displacement equation, and then actually get the maximum displacement.
Does that always work? The y max is...
No, you have to be a little careful because you'll notice this equation is a cubic equation. So finding the roots of a cubic, there's going to be 3. And probably only 1 is going to be in the range between x equals 0 to L. You might find another one outside the range. Or in our case, if it's negative, that doesn't really make any sense. If it's imaginary, that doesn't make any sense for us either. So you can probably eliminate it. So one thing you could do is just look, logically it's going to happen somewhere in the middle. Even if the load is a little bit asymmetric, it's going to kind of move towards the higher end of the load. So you have a range that you know it'll be in. You could kind of look for it. But again, it's not a trivial problem finding roots to a cubic, like in the middle of an exam. Probably wouldn't expect you to do that. But for homework, hey, you got all kind of time and resources. It'll be home fun too. So any questions about that one? Okay.